What can we do with them? Let's see what we can do. Any questions before we move on? Anita, you have any questions? No? Okay, let's find out ways on how to approximate and simplify this sum of the integrals. And let's talk about the asymptotic expansion of integrals. And we also try to inject physics into our mathematics. We'll first talk about the mathematics first and see what kind of physical insight we can gain from the mathematics. Okay? So there are a few mathematical procedures or methods that we need to learn. One is the method of stationary phase. So if we have an integral that looks something like this, somewhat like a Sommerfeld integral. Okay, this is not a time variable, this is just an arbitrary variable. It has the property that this g lambda t can be simplified. This means asymptotic to. This is a notation meaning asymptotic to. Okay? That this can be simplified into an exponential function. When there is a large parameter that becomes very large, like in our case will be frequency, or 1 over wavelength, or k, the wave number k. So lambda can be omega, can be k. It becomes very large. What can we do with this integral? Well, we can apply the method of stationary phase to simplify this integral. Let's assume that this h function has this very special property that if I were to plot it, this is a real plot now, okay, not the complex plane, because I drew so many complex planes in this course. When they start to label the x and y axis, you think that it will be the complex plane. This is a plot of the function h of t. Let's assume that it looks something like this. So it has a stationary point at t equals t naught. Okay, it's a stationary point. And if you were to look at g function instead now, if lambda is very large, g function will look something like this as a function of t. G is a complex function, but I cannot plot complex function, but just look at the real part of g. And it will look something like this, because lambda is very, very large. So when h changes a little bit, g will change very quickly. So g actually becomes a rapidly oscillating function of t. Because any small changes in t or h will give rise to a rapid variation in g. But that happens at all points except that at this point it varies less rapidly. It varies slowly. So if I were to plot this oscillatory function, it will look something like this. Roughly, this is how it looks like. If we take the real part of this highly oscillatory function, slowly varying, slowly oscillatory about this stationary phase point. This is also called a stationary phase point, but highly oscillatory away from that. What this tells me is that if I were to perform this integral on a computer, this would be a very hard integral to perform. Because as lambda gets bigger, the integrand gets more and more oscillatory. And it's extremely hard to perform this integral. And this is just the Marr case that I have drawn. It can be actually like this, right? Then you will have to integrate very finely and do a lot of very fine integration points in order to capture this integral. So numerical method is like an uphill battle. And we better think of something clever to say about this integral. We say that this integral is so rapidly, or this integrand is so rapidly varying, that as we integrate, the plus and minus sign of this integrand will just cancel each other. Okay? If we try to integrate the function, goes plus and minus in a regular fashion, all the contribution will go to 0, except for around this point, when the cancellation is not there, because somehow the thing slowed down, so the cancellation is not there. So I would argue that when I integrate this function on the real axis, most of the contribution will come from here. The rest of the point, the contribution is very small due to destructive cancellation. Okay, they just cancel each other. So I can say that I can approximate this integral with ft being a constant value. Since this is going to be having contribution mainly from this point only, so this function is actually behaving like a delta function having some shifting property of some sort, because it causes the contribution to this integral coming from only a tiny point at t0. So I might as well approximate this slowly varying function. This is slowly varying. It's not affected by lambda. If you make lambda very large, only this becomes rapidly varying. I'm going to take that ft out and then evaluate at the point where it contributes the most, and then just integrate the rest. Okay, that should be true. And this should be true when lambda becomes very large. Yes? Sorry, it should be over t. Yeah, it should be over t. Thanks for pointing that out. So it should be true, right? So if I can find a closed form for this, then I'm all done. So the trick for this method is that if you have an integral that looks very complicated, try to separate it into a slowly varying part, the slow part, and then the rapid part. Okay? And then try to find a closed form integration for the rapid part, and take the slow part and put it outside the integral. Then you have an approximation for the complicated integral. Okay. Let's see how we can do this for a sum-of-all integral of some sort. And we say that this is what we encounter in one of the sum-of-all integral, minus infinity to infinity decay rho, k rho cubed over kz h01 k rho e to the I kz3. Let's see how we can find an approximate solution for this integral. We know that this integrand will be rapidly oscillating because this function has this asymptotic behavior. When k rho tends to infinity, or rho tends to infinity. Okay, you can keep k rho fixed, but when rho tends to infinity, you have this behavior, which means that this is highly oscillatory. If rho is very large, k rho just have to change a little bit, then the function changes rapidly. This part too is also highly oscillatory. If z is very large, if kz changes very little, or kz is k squared minus k rho squared. If k rho squared changes very little, this function will also become highly oscillatory. So this actually is a very good candidate for the method of stationary phase. It's highly oscillatory, and can we do something to evaluate this very rapidly? So we know that the integrand will look something like this. Okay, integrand will look something like this. When, sorry, kz when rho z tends to infinity. This is approximately how the integrand will look like. So we have to find out when this will become stationary. Okay. What the corresponding T0 point is, and then apply this method. I guess we don't have time to do that, complete the discussion this lecture, but we'll do that in the next lecture. And look at the method of stationary phase and try to give it physical interpretation. What does it actually mean physically? Okay, that you don't get in many textbooks. In many textbooks, just teach you the technique and then give you the interpretation. We'll meet again on Thursday at 9 a.m.